happens when we electrify our public transportation system, but completely forget to engineer the infrastructure to support it. As of 2025, there are already over 11,593 E-PUVs moving Filipinos around the country, and with government programs like the PTMP, this number will only keep rising. But here's the real challenge. Our transportation isn't failing only because of too few chargers, they're failing because of uncoordinated charging. Right now, stations often charge batteries and cars at random, without considering grid conditions, city prices, or actual demand, and it's dominated by charging instead of swapping. This creates three problems at once. Firstly, strain on the power grid. Secondly, higher costs for operators. And lastly, long waiting times for commuters. We realize the key isn't faster charging or building more stations. It's smarter scheduling. With the 349 battery swapping stations already operating today, we don't need more infrastructure. We just need to work with what we have and make each one smarter. Hi, I'm Ira Noel Concepcion, introducing eSwap, smart battery swapping stations for E-PUVs. eSwap is a smart battery management system that integrates real-time demand forecasting, electricity pricing optimization, and battery health prioritization through a predictive control framework. To put it simply, it is a code that can be integrated into existing battery swapping stations that decides 1. Which batteries to charge, 2. When to charge them, and 3. How long to charge them for. eSwap operates on this flow. First, data collection. Second, demand forecasting, then optimization, refreshing every 30 minutes. First, we collect all the pertinent data for the algorithm, like electricity prices from the WESM spot market, jeepney routes through cooperatives and LGUs, battery specifications from the manufacturers, and battery state through the BSS or battery swapping station itself. We then need to predict how many batteries will be needed by the E-PUV fleet. We do this by forecasting the battery demand over the next 8 hours, split into 30-minute intervals with this formula. Travel time predictions from Google Maps API, the number of jeepneys currently deployed, and battery specifications are plugged into this model to create the battery demand curve. This demand curve tells us how many batteries are needed every 30 minutes for the next 8 hours. eSwap forecasts the next 8 hours of demand, but it continuously updates such that we have a new curve every 30 minutes. This demand is then fed into linear model predictive control, which works by creating an optimized charging schedule based on the first interval of the forecasted demand curve using this formula. The constraints here serve to preserve the health of these batteries whilst meeting the demand. After 30 minutes, a new charging schedule is generated based on the new demand curve. This allows it to adapt in real time to traffic, grid prices, and fleet movement. With a smarter battery swapping system, operators save money, no longer paying for batteries that make up 40% of an EV's cost only to degrade over a few years. Commuters benefit too. Faster swaps means E-PUVs spend less time charging and more time moving people, with lower operating costs, possibly translating to lower fares. As for the Philippine grid, off-peak charging helps cut electricity costs, ease grid strain, and build a more sustainable, reliable transport system for everyone without compromising our already strained energy grid. If you're not convinced by now, why should you believe in eSwap? First, for its novelty. There are already other smart charging algorithms available, but none of them cater towards battery swapping. eSwap is the first smart charging algorithm for battery swapping stations specifically catered to E-PUVs. Second, for its relevance to the Philippine context, it tackles the key issues that hold back the widespread adoption of E-PUVs, addressing the high operational costs, the inadequate charging infrastructure, and the need for better energy management, all of which address the concerns surrounding the PTMP. Third, for its feasibility, eSwap is compatible with existing infrastructure, which means we don't need to rebuild the charging stations. What we need most are the data partnerships and connections to these battery swapping stations for implementation. And lastly, for its scalability and sustainability, it can be applied to all battery swapping stations with the proper software and can integrate future features like renewable energy integration. Meanwhile, also promoting sustainability by improving the efficiency of current EV infrastructure and reducing reliance on backup diesel charging. This system doesn't just swap batteries, it powers a smarter, cleaner, and more reliable transport future. With eSwap, we don't just follow progress, we engineer it. Let's go eSwap!